All right, so we're reviewing logarithmic graphs, etc. So we're going to look at log base 2 of x. If we want to sketch it, we have to make sure we type it into our calculator. Now remember, you can go log base 2 of x using the math button, or if you have the older calculators, you're going to have to type it in as log x divided by log base 2, like this. Anyways, when we put that in, we are going to get an asymptote, vertical asymptote on the y-axis because there's no transformations. The only thing that moves the asymptote is a horizontal translation, which there isn't one. It is the y-axis, so that's the equation x equals 0, and it is a vertical asymptote. So we'll do this one in red. So I have 1, 0. Okay, so we're at 1, 0. And then we're at 2, 1. And then we're at 3 and 1.5. 8. And we're at 4 and 2. 5 and 2.3. 6 and 2.5. 7 and 2.8. 8 and 3. 9 and 3.1. 10 and 3.3. 11 and 3.4. 12 and 3.5. Now these ones are easy to connect, but then people just go and draw a random thing. Because at 0 it says it's undefined. But remember, we can go second trace value and go 0.5 and get something else that isn't undefined. And it's at negative 1. 0.5 is at negative 1. And then say we do second trace value 0.25. At negative 2. And it's going to run down the graph. So this one is an increasing log function. We'll do the other one in blue. Remember, you can put this in using the math button, or you can go log x divided by log a half. If you have the older calculators, I would just use the math log base button if you have that option, just because it's easier. Into your y equals. So I'm going to go by 2, and then an x, and then I'm going to go second graph. And now, once again, I am at 1, 0 starting, the first one that shows me, and then 2, negative 1, at 3 and negative 1.5. We're starting to see commonality here. 4 and negative 2, it's a reflection. 5 and negative 2.3, 6 and negative 2.5. Let me reset my whiteboard, smartboard. It's not putting it where I'm putting it. 2.8, 8 and negative 3, 9 and negative 3.1. So it's literally reflecting. Negative 10 and negative 3.3, 11 and negative 3.4, and negative 3.5. Let's pretend that those are curving correctly. So when you have log base 2 and log base a half of x, they are literally just reflections. The half makes it a decreasing log function. So if this one's at 0.5 and negative 1, it's going to be at 0.5 and 1. And if this is at 0.25 and negative 2, it's going to be at 0.25 and 2. It's going to curve and run along. So that's a decreasing, because you read from left to right. So it's a decreasing exponential. Kind of went through the dots, but I just didn't do. And then the red is an increasing. Okay. So we're going to look at logarithmic transformations. Now remember, the base actually doesn't matter in the fact that if you compare them, really what we should do is we should say, okay, from the original graph, y equals log base 3 of x. It's transformed to this. So the base 3 needs to be the same. And for b, you would have y equals log base 1/2 of x, because the base stays the same and doesn't appear anywhere in your transformations. Okay? If your bases aren't the same, you had a reflection in the x, correct? So really, you could just put a reflection in the y and flip the base if for some reason they give you a half and the other one was 2. But I don't really see that too often. So the first thing we have to do when we do transformations is we have to get y by itself. So we're going to go y equals negative log base 3. It already is by itself, but we also need to make sure we have a 1 in front of our x. Currently we have a 2. So we take the 2 out and we're left with x plus 3. Because 6 divided by 2 is 3, minus 3. So our transformations we have do stretch, reflect, translate. We have a horizontal stretch by a factor of 1/2, because it always flips, about the y-axis. We have a negative in front, so we have a reflection in the x-axis. Our translations, we have a horizontal translation three units left. Because it's a plus 3. And we have a vertical translation three units down. Now, if we look at the equation of the asymptote, remember that log graphs have vertical asymptotes. So normally it's along the y-axis. So the only thing that can move that is a horizontal translation. So with a log graph, your horizontal translation is your vertical asymptote. So here we have a vertical asymptote. And normally it's at x equals 0, but this has been moved 3 to the left. So it's a vertical asymptote at x equals negative 3. The graph has been moved 3 to the left. So it's x equals negative 3. Now your graph is normally x is greater than or equal to 0. The only time it's less than is if you have a reflection in the y-axis, which means we have a negative in front of our x. But in front of our x, we actually have a positive. So it's not going to be less than or equal to. Our domain is still going to remain greater than because we don't have that reflection. It's an x, not a y. Okay. X such that x is greater than, and our asymptote, negative 3 XER. Our range of a log, they go completely up forever and down, or up, down forever and up, whether it's increasing or decreasing. So it's going to be y such that y is none of the reals. Now in interval notation, this one here is going to be less than negative 3, or greater than negative 3, sorry. So it's round bracket negative 3 to infinity round bracket. And then YER is just negative infinity to infinity in interval. The x and y intercepts. So if I want an x-intercept and a y-intercept, to get the x-intercept, I set y equal to 0. So I'm going to go y equals negative, I'm just writing it down, negative log base 3 2x plus 6 minus 3. So I need to set y equal to 0. So I get 0 equals negative log base 3 of 2x plus 6 minus 3. So the first thing I have to do is add the 3. So I need to get the log by itself so I can convert to exponential. So I get 3 equals negative log base 3 2x plus 6. I still don't have a log by itself because I have this negative 1 sitting in front. So I'm going to divide by negative 1. And I get negative 3 equals log base 3 of 2x plus 6. Now I have a log by itself, a single log, so I can convert to exponential. So I'm going to go, the base of my log becomes the base of my exponent. It's raised to what it's equal to, and it equals what's beside the log. So 2x plus 6, don't know why I just put it in brackets, that's okay. 3 to the negative 3 is 1 over 27, equals 2x plus 6. Subtract 6, and we get 1 divided by 27 minus 6 is negative 161 over 27 equals 2x. And we're going to divide by 2, that whole fraction, and we get negative 161 over 54. So it's negative 161 over 54. 0. The y-intercept is always the easier one to find. Y-intercept x equals 0. So we're going to go y equals negative log base 3 of 2 times 0 plus 6 minus 3. So we get y equals negative log base 3 of 6 minus 3. So we have to make sure we close that bracket when we type it in. So we go negative log base 3 of 6 and close that bracket minus 3, and you get negative 4.63 approximately. So 0 and negative 4.63. All right, let's go back up here. So now we have to state the transformations for this one. We have to remember to take, oops, I just smoked my smartphone. We have to remember to take a fraction out, so we're going to get y equals 2 log base 1/2. Negative 1/3 out. When I take a fraction out, it actually gets bigger, remember? Because when you divide by a third, it's like multiplying by 3. So you get x plus 6. If you do 2, sorry, it's negative 2. Negative 2 divided by a negative 1/3, if you were stuck, you could always type into your calculator. When you do that, you're going to get positive 6. Okay, so let's do our transformations. We have a vertical stretch. You could do horizontal first, it doesn't matter. Vertical stretch by a factor of 2 about the x-axis. You have a horizontal stretch by a factor of 3, those flips, about the y-axis. The negative is with the x, so it's a reflection in the y-axis. And then we have a horizontal translation units left, and that's for the opposite way. Now remember, your asymptote is going to always be, if it's a log graph, the horizontal translation. If it's an exponential graph, it's the vertical translation, because an exponential graph has a horizontal asymptote. All right, so I'm just typing it in, so in double check. Okay, so we normally have an equation of an asymptote at x equals 0. It's now going to move 6 to the left, sorry. So we have a vertical asymptote. 6 to the left. So it's at x equals negative 6. Now, normally my domain is x is greater than negative 6, but if you look here, I use this yellow, if you look here, there is a negative sitting there in front, which means we have a reflection in the y-axis. We have a reflection in the y-axis, my greater than sign is going to turn less. So my domain is going to be x such that x is less than or equal to, not equal to, sorry, that's the asymptote that, less than negative 6 xer, or in integral notation, negative infinity to negative 6. My range is still yer because it's a log. Okay. My x-intercept is going to be when y equals 0. So it's the uglier one. The equation is, I always put it into the one that's, I didn't pull the horizontal stretch out of, so it's going to be y equals 2 log base 1/2 negative 1/3 x minus 2. Okay. So I'm going to fill 0 in for y, and I get 2 log base 1/2 negative 1/3 x minus 2. And I can't solve this until I get a log by itself, then I can convert to exponential. So I'm going to divide by 2. When I divide 0 by 2, I get 0 equals log base 1/2 negative 1/3 x minus 2. Now I have a log by itself, so I can convert to exponential. 1/2 to the 0. So the base of my log becomes the base of my exponent. What's with it doesn't stay with it, so it's going to be the power of 0. And it equals negative 1/3 x minus 2. Now anything to the power of 0 is actually 1, not 0. So I have 1 equals negative 1/3 x minus 2, and 2. I'm going to get 3 equals negative 1/3 x. And then I'm going to multiply by negative 3. So x equals negative 9. So negative 9 and 0. And a comma. Okay, my y-intercept, I've already looked at the graph, so I know my y-intercept actually doesn't exist because the graph is completely less than negative 6, right? So it's up here, it shows that. So it's not going to cross the y-axis. So let's show why. So your y-intercept x equals 0, so I'm going to get y equals 2 log base 1/2 negative 1/3 times 0 minus 2. So I'm going to get y equals 2 log base 1/2 of negative 2. Now you can't take the log of a negative number. You cannot or can't take the log of a negative number or 0, but in this case the negative is the issue. So there is no y-intercept. Okay, next page. Okay, here we have exponentials. Now, I told you when you get exponentials with one exponent, you can contemplate converting to a log. But if you have an exponential with 2 exponents, you either try common base, and if you can't do common base, then you log base 10 both sides. Well, this one here, I can make all be base 5, so I can do the first method by common base. So 125 is 5 cubed. 2x plus 1 equals 5 to the 1. Make sure you put it to the 1 or you're going to forget to add that 1. And then 25 is 5 squared to the 3x plus 1. So I'm going to get 5 to the 6x plus 3, don't forget to distribute, equals 5 to the 1 times 5 to the 6x plus 2. Now I can't drop the 5's off until I have 5 to an exponent equals 5 to an exponent, so I need to put these together first. So I'm going to get 5 to the 6x plus 3 equals 5 to the 6x plus 3. These are the exact same function. So if I go 6x plus 3 equals 6x plus 3, if I do that, I actually get no solution. You type them in your calculator and see if they ever cross. If they don't cross, then there's no solution. Okay, this one has one exponent, and the 3 and the 24 both don't have exponents, so you have to remember that it's like having an initial in your word problem. You can divide that 3 over. So we get 4 to the 2x plus 1 equals 8. Now you could make them the same base, or you can convert to a log. I'm going to convert to a log. So the base of my exponent becomes base of my log, so log base 4, what's with it doesn't stay with it, so it's going to be of 8, equals 2x plus 1. And I need to isolate x, so I'm going to subtract 1, so I get log base 4 of 8 with a closed bracket minus 1. This 1 does not join the 8, equals 2x. And then I'm going to divide by 2. And then I'm going to type it in my calculator. Remember, you can y1, y2 all of these. You can y1, y2 all of them. So you get a quarter. And we can check them back. We can go 3 and then go 4 to the power of 2 times a quarter plus 1 and see if you get 24. What you do, so you checked it and it works. Okay, when you have a single log, you will have to get the single log by itself. We just talked about this. When you get the single log by itself, we're going to have to divide by 2. Or we could raise the 2 as the exponent. It doesn't matter, but when it works out evenly, I always just divide it over. So I get log base 6 of x plus 2 equals 2. Now I have a single log and 3 pieces of information I can convert to exponential. So the base of my log becomes the base of my exponent. What's with it doesn't stay with it. So 2 becomes my exponent, and it equals x plus 2. Subtract 2. And so I'm going to get x equals 36 minus 2. So x equals 34. Once again, I can y1, y2, but I need to make sure my x max is at least 34 in my calculator, or it will error me. Okay, this is one where I have 2 exponents and I can't make common base. When that happens, I have to log base 10 both sides. I told you we'll have one of these on your test. So it's log base 10 of 4, and then I put a dot to make a point of showing that I'm multiplying so I don't mess up in the second step, because I told you, you can get your second step right, most people will do the question right. So 4, and then x plus 2 equals log base 10 of 9 to the 2x minus 3. So I have to separate this by addition, because that's what you can do with multiplication. Log base 10 of 4 plus log base 10 of 7 to the x plus 2 equals log base 10 of 9 to the 2x minus 3. Then my rule was I could take my exponent and drop it in front. So I'm going to get log base 10 of 4 plus x plus 2 times log base 10 of 7 equals 2x minus 3 log base 10 of 9. And I have to distribute. So I get log base 10 of 4 plus x log base 10 of 7 plus 2 log base 10 of 7 equals 2x log base 10 of 9 minus 3 log base 10 of 9. Now I have to get my x's together, and the other one's the other side. So I'm going to minus log base 10 of 4 over. I'm going to minus 2 log base 10 of 7 over. So those cancel. And then I'm going to minus 2x log base 10 of 9 over. So I'm going to get x log base 10 of 7 minus 2x log base 10 of 9 equals negative 3 log base 10 of 9 minus log base 10 of 4 minus 2 log base 10 of 7, and then I divide it over. Take an x out, and I'm left with log base 10 of 7 minus x, 2 log base 10 of 9 rewrite this. Then divide it over. So I'm going to get log base 10 of 7 minus 2 log base 10 of 9. And then we're going to plug in our calculator. When you type it in, you get x equals 4.85. And you can y1, y2 the original. So I scrolled it down a bit. You can y1, y2, second trace 5, enter, 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 and you get the same answer. Now, when we have log base 2s, we have 2 different ways we can do this. We can make them all be log base 2, which is the option I usually choose off. So I go off to the side and I say 2. I need 2 to equal log base 2 of something. Because if I can get this to be log base 2 of something, then I can replace it. So what you do is you go log base 2 of something gets me this. So if I take what's here and I raise this to that exponent, so 2 to the 2, I get 4. So actually, 2 equals log base 2 of 4. So now instead of having a 2 here, I can replace it. So I'm going to go log base 2 of 3x plus 1 equals, and instead of this, I'm 2, I'm going to have log base 2 of 4, because that means the same thing, and it's base 2, minus log base 2 of x minus 1. Now I can put them together if they have plus or minus 1s in front, which they do. So this side I'm going to leave as log base 2 of 3x plus 1. And then this one's going to become log base 2. 4 is going to go in the numerator because it has a plus 1 in front. This one has a minus 1 in front, so x minus 1 is going to go in the denominator. I now have log base 2 of this equals log base 2 of that. So if that's true, I can just say 3x plus 1 must equal 4 over x minus 1. And now I can multiply by my x minus 1. Which is going to get me a quadratic. So I'm going to get 3x squared plus x minus 3x minus 1 equals 4. I have to move, whenever I have a quadratic, I have to move everything to one side. So I get 3x squared minus 2x, and then I subtract the 4 over, so I get minus 5 equals 0. And then I have what multiplies to give me negative 15 and adds to give me negative 2. What times what equals negative 15? What plus what equals negative 2? It's going to be negative 5 and positive 3. And 3 would go better with 3, so I'm going to go 3x squared plus 3x minus 5x minus 5 equals 0. Through. Put a plus sign in the middle. I get 3x, x plus 1. Take out a negative 5. I get x plus 1. So my two factors are x plus 1 and 3x minus 5 equals 0. So when I solve them out, I get x plus 1 equals 0. 3x minus 5 equals 0. Subtract 1. X equals negative 1. And then add 5. 3x equals 5, divide by 3, x equals 5/3. And then I have to always check with logs that when I plug it back in, I don't get a negative. So if I take the negative 1 and I plug it into here, I get way up here into the question, and way up here. 3 times negative 1 plus 1 is negative 2. Can I have a negative 2 beside? No. So what do? I circle it, I put a line through it, and I say extraneous. Remember that? And then I try 5/3. 3 times 5/3 is 5 plus 1, which is 6, so it would be good here. And then if I try 5/3 here, 5/3 minus 1 is also a positive number, so this one works. Remember, you can also y1, y2 that and check. This one here is all logs, so it's in a really good roll already. So I just have to make sure the logs have 1s in front, which they do, and then I can put them together. Okay? So I can go, there's log base 5, so I can put them together, plus 1, minus 1, so I can put them together. So I'm going to get log base 5. On the top, I'm going to get x minus 18 because it has a plus 1 in front of the log. In the bottom, I'm going to get an x because it has a minus in front of the log. And on this side, I have log base 5 of 7. Now, if I have log base 5 of this equals log base 5 of this, I can set them equal. So I can go x minus 18 over x equals 7. And we do the same thing we did before. Multiply by x. X minus 18 equals 7x. This one's nicer than the last one because it's not a quadratic. I can just subtract the x over. And I get negative 18 equals 6x. Divide by 6. X equals negative 3. Now, just because it's negative doesn't mean it's wrong. So we always have to check and make sure that it actually doesn't work. So if I take the negative 3 and I plug it in, I get negative 3 minus 18 up here, and I get minus 21. So it doesn't work. So we circle it, put a line through it, say extraneous, and no solutions work. There's not one. So if you put in your calculator and try and press math, enter, enter, it's never going to work because there's no solution. So if a solution doesn't work, it's just extraneous. But if it's the only solution and it's extraneous, then the answer would be no solution. We're going to flip over. So this one here, I told you when you have logs embedded in a log, when you have a log embedded in a log, you basically have to convert to exponential however many times it's embedded. So what I do is remember I told you I'm going to put a line through this just to pretend it's not there for now. And I'm going to go 5 to the 0 equals what's beside, equals that red line. I treat it like it's a whole thing. So 5 to the 0 equals log base x of 2x minus 3. That's what's hidden behind this red line. Because I treat what's in this red line here, let's go like this. This red line here, what's here, actually is what it goes beside. So it's 5 to the 0 equals that big log. 5 to the 0 is 1, so I get 1 equals log base x of 2x minus 3. So there's one log, there's two logs embedded, so I'm going to have to convert twice. So now I have one log left. So now I'm going to go the base of my log becomes the base of my exponent. What's with it doesn't stay with it, so it's to the 1 equals 2x minus 3. And I'm going to subtract my 2x over. And I get negative x equals negative 3, divide by negative 1, x equals 3. And then remember, not only can what's beside a log not be negative, the base can't be negative. So when I go to plug it back into this equation up here, I'm going to go here. I'm going to plug it back into that x, and it's a 3. So that's good. Then I'm going to plug it in for this x to see if I have a positive beside my log. 2 times 3 is 6, minus 3 is 3. So this works. It's the answer. We're going to skip this one because it has trig, and we haven't learned trig yet. Usually we do trig first. So we're going to skip that one. So we're going to go to this one, and it's using all the rules that I talked to you about. So remember when I said you get log base c of c to the 4? When these are the same, the answer is just the exponent, so it's 4. Log base c to the 4, your answer is 4. Minus log base 6 to 36, you could type into your calculator. If not, you could say 6 to what exponent is 36? It's 2, so the answer is 2. I also told you this, if the base of your exponent is the same as your base of your log, and the log is the exponent, your answer also is just the number beside the log, so it's 3. And then when you have beside a log always 1, you'll say k to what power is 1? It's 0. So even if I had like log 6 to the 1, my answer would be 0, because 6 to what exponent is 1? 0. If I had log a quarter to the 1, a quarter to what power is 1? 0. So anytime beside my log I have a 1 by itself, my answer is going to be 0. So I'm going to subtract 0. So I'm going to get 4 plus 3, which is 7, minus 2 is 5. Let me go down to this one. This is the one that we talked about. I've given you a whole bunch of times. I told you that you're going to look over. It's going to give you a piece of information. So it's going to say log b is 30 of 36 is 2. Log c of 125 is 3. And then it wants log 1000 bc. Okay. So these ones you could split, but the base of them isn't a b, correct? So what we could try is, I'll show you the one where it is the way we've normally done it. This one, the base isn't b. So what you can do, I'm going to show you this one. You can go log, you can rewrite this as log base 10, because remember it doesn't have base per 1,000, plus, these are all multiplied, log base 10 of b, plus log base 10 of c. Log base 10 of 1,000 is 3. Okay. Now the b and the c we can solve. These ones aren't in the base 10 like the other ones we normally deal with, but we can convert this. Base of my log is b, to my exponent is 2, equals 36. And then I can take the root of it, and b equals plus or minus 6, but because it's in the base, it has to be just 6. Because I can't have a negative down here. Then I do the same with the c. C to the 3 equals 125, I convert it. I take the cube root of c and the cube root of 125, and I get c equals 5. So now in for b, I can put 6, and in for c, I can put 5. So I'm going to go plus log base 10 of b, which is 6, plus log base 10 of c, which is 5, and then I can put them together. So I get 3 plus log base 10 of 30. So this is a little different than what we did before. I'll show you the one we did before. So p would be 3, and then r would be 30, and they want 3 plus 30, so my answer would be 33. What we did before was more like this. I would give you log base 3, not 3, sorry, log base a of 3 equals x. And then I would give you log base a of 5 equals y. And then I would tell you to determine log base a of 75 a squared. Now, I have log base a of 3, not a of 75, and I have log base a of 5, not 75. but how can I maybe make 75 be 3s and 5s? So I know that 75 is 3 times 25, so I can go 3 times 5 times 5 instead. So I can go 3 times 5 times 5 times a times a. These are the type of most normally did. So it can come up. So when I have multiplications, I can go log base a of 3 plus log base a of 5 plus log base a of 5 plus log base a of a plus log base a of a. Now we know that log base a of 3 we have over here is x, plus log base a of 5, which is y. So then log base a of 5, which is y, and then log base a of a is 1, and 1, so I'm going to get 1 plus 1. So my answer would be x plus 2y plus 2. That's if I did it the other way, where it actually was the base of the logs that they gave me. Then there's these 2 word problems. We're going to do them on Monday. I'm not going to make you do them right now. I just want you to do up to where we just got.